Welcome to a lesson with Dr. Powell. Let's talk about a way that we can approximate a definite integral. So definite integral represents the total change of an antiderivative. It also represents the exact area under a curve because it's the change of an antiderivative, and the area function is an antiderivative. Now, let's take a look at the idea of change of an antiderivative or change of a function. Let's call the antiderivative that we're interested in capital F of x. All right. And this change of y is going to be a change of the output, the y values of this function, capital F. Suppose it's the curve of capital F. Now, thinking about a change, assuming that this has a derivative, which it does, because it's an antiderivative, then we can approximate our change of y by dy. What is dy again? dy is the change of y of the tangent line of the curve. So in particular, like this case, let's suppose we have an x value of x1. Let's take the tangent line right at x1, kind of at the beginning right there. So dy would actually be the change of y over the interval from x1 to x2. Notice that, at least in this case, it's going to be a little bit more to get to x2 there. So it's a little bit greater. But the idea is, at least if you're small enough, as you close in this gap, this difference between x1 and x2, then dy is going to be closer to change of y. And it's going to be approximately the same thing. Now, we know that the ratio between dy and dx on that interval is equal to the slope of the tangent line right there, which is f prime of x1. You can rearrange this as dy is equal to f prime of x1 times dx. I just drew this little line just to remind us that we're focusing at the point x equals x1. Okay, so we can approximate this change of y here on this little interval. But what if we did this over lots of intervals? Like we approximated the change of y here, 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 and we added the results. So this is a sum right here of change of y's, and that's going to be equal to the total change in y, maybe on a larger interval. Now, as long as the subintervals, the small little parts where we're taking our change of y's and approximating with dy's, if those are small enough and we have this and we're kind of thinking change of y is approximately dy, it seems reasonable enough that this sum would be approximately equal to the summation, or the sum of all the dy's. And all those dy's, remember, look something like this, like f prime of some x value with regards to that specific interval. I'll just put a star there, times dx. And we're just kind of adding up all of these guys right here. This looks a lot like the integral notation. In fact, if we just replace that summation with this integral symbol, it looks pretty much the same. I mean, this is notation, but it also has a lot of meaning here. So pretty much what we're doing when we're adding up all the changes of y, we're adding up, we can approximate that by adding up these dy's, which is the same thing as adding up these guys right here, namely the value of the derivative in an interval multiplied by a little dx, which is just the length of the interval that we're subinterval that we're working with. Kind of, now you see what this is right here. Let's suppose that this graph right here is now, this curve right here is actually f prime. Then this is like a height times a width. So dx times a height right here. And we get a sum of rectangles right here. Now, so we're taking a sum of rectangles, and this sum of rectangles approximates the area under the curve of f prime, which we know that the area under the curve of f prime actually ends up being exactly the change of y, or the definite integral itself, which we're trying to approximate. So kind of the idea of approximating this, the change in y, by using lots of dy's, is the same thing, in using this particular formula here, is the same thing as approximating exact area by sum of rectangles. It's one and the same thing. So we're using a linear approximation, like a tangent line approximation on little subintervals, and then adding up the results. How far we're off is the same amount that we're off as if we were to take a sum of rectangles, of areas of rectangles, and compare it to the exact area. Visually, you can imagine that if your intervals are smaller and smaller and smaller, so the rectangles are skinnier and skinnier and skinnier, this approximation will get so close, in fact, it'll converge to and limit to the exact area of this. So one method of approximating a definite integral is actually by taking sums of rectangles in such a way. That's called taking a Riemann sum. This is very useful, especially if it is challenging and and even impossible at times to find an antiderivative to actually use. Sometimes we just know a derivative, but we do not know where it came from, what function it came from, and formulaically, it's too hard to actually determine it. So how do we work with that in that situation? That's where we need something like Riemann sums to approximate, namely just sums of areas of rectangles. Thanks for watching.